Hello, welcome back. So in this part, we will discuss about the steps that we use to design the doubly reinforced beam. Well, here I would say that most of the steps that we have followed in the lecture 11 while designing the singly reinforced beam, most of the steps are same. The only added things will be because we have added the compression reinforcement. So the steps related to the compression reinforcement will be added here. So as I written here also that all the steps of designing doubly reinforced beam will be the same as that of singly reinforced beam. And as we have provided the compression reinforcement in the doubly reinforced beam, so we need to learn how do we find out the or how do we calculate the area of reinforcement for the compression part. So that is the added thing. So in this case, we will try to learn how do we find out the compression area, area of compression reinforcement. So in the previous lecture, I have discussed about the moment of resistance, and we know that moment of resistance is the summation of M1 and M2. Now, what is M1 and M2? This I have already discussed in the previous lecture. Well, M1 is the moment of resistance of singly reinforced beam as a balanced section. And we know moment of resistance for singly reinforced beam as a balanced section can be given as, or we can write this simply as RBD square. So this RBD square will be for balanced section for singly reinforced beam. So M1 value can be calculated as RBD square. And M2 can also be calculated in this manner. If we know the M value, then M2 can be calculated as M minus M1. So M2 can be calculated as M minus M1, and M1 is further elaborated as RBD square. Now, to calculate the reinforcement, we are required to have moment of resistance. As you know, in case of singly reinforced beam, when we used to find out the AST, the formula for AST was M by sigma ST into J into D. So this is the formula that we used to have. So in this case, we are required to have moment. So in the same line, we are supposed to have moment M1 and M2 to calculate the area of steel in tension and in compression as well. So basically, if we talk about the AST, well, we know that this is the AST1, and in case of imaginary section, this will be AST2, and this will be ASC. Okay, so we are supposed to find out AST1, AST2, and ASC. So we will see how do we find out AST1, AST2, and ASC. So now, as we know that AST is the summation of AST1 and AST2, but we need to find out the AST1 and AST2 separately because they are basically the product of a different entity. So with the diagram, we will try to understand how do we find out AST and AST1 and 2. Well, as I discussed earlier in the previous slide, that AST1 can be simply calculated as we calculate in the singly reinforced beam, as in the case of singly reinforced beam. So this is M by sigma ST into J into D. So this J into D is actually the lever arm. So in the diagram, you can see this one is the lever arm. So if we multiply C into lever arm or T into lever arm, then we find out the moment of resistance of the singly reinforced beam. And with that, we can find out the AST1. Well, on the same line, using the same formula as M2. So to calculate the AST2, if we place M2 in place of M1 and sigma ST will be as it is. And in case of lever arm, well, lever arm is actually the difference between the compressive force and tension force. As you can see, in the case of singly reinforced beam, the compression is borne by the concrete part. So this much part of the concrete will bond the compression. And if we see, if we look at the stresses, this line, this area will be experiencing the maximum stress. So this is the FCBC. Okay, and at the neutral axis, the minimum stress will be there. So the stress will be varying like linearly, and this is how we find out the triangular part of the stress. I mean, this is the variation of the stress across the depth of the beam up to the neutral axis, and the compressive force will be at the CG of this triangular area. So the compressive force which is borne by the concrete will be acting at x by 3 distance from the top. So the distance between C and T is called lever arm. So this is the lever arm that we are using to calculate AST1. Similarly, now when we are talking about the AST2, now what will be the lever arm in this case? As you can see in the second section, this is the position of the ASC, which is, I mean, the compression reinforcement, and this is the position of the tension reinforcement. So this compressive reinforcement will offer or will resist the compressive force, which we are again representing as C, and this C will be acting at the CG of the reinforcement. So CG of reinforcement will pass through the center line of the reinforcement. So on the same line, you can see this is, I am extending this as this. So in case of tension, again the tension force will be acting at the CG. So again, so the distance between these two, C and T, will be the lever arm, and lever arm in this time will be D minus D dash. Well, D dash is the effective cover of the compression reinforcement. So this time this will be the D dash, I mean the lever arm. So the same value I am putting here, and so this becomes the formula to calculate the AST2 value. So this is how we can calculate AST1 and AST2. Now we are going to see how do we find out the area of steel in compression, which is ASC. Well, area of steel in compression, which is ASC, it can be calculated by two ways. First way is by equating the C and T due to ASC and AST2. So as I discussed just now, that this ASC will be offering C and this AST2 will be offering T. So if we equate C and T, then we can calculate the value of ASC. Well, C is the compression force offered by the ASC, compression resistance offered by the ASC. So this is actually the force. So we know that force is stress into area. So when we write the expression for C, then this becomes stress into area. So stress in the steel, that is ASC, we represent this as FCBC dash. I hope you remember in the previous lecture I have used this value FCBC dash for the stresses in the compression steel. And area of the ASC in terms of concrete, which we call equivalent area of the concrete, we will write here. So which will become 1.5 m minus 1 into ASC. So this is also, I have explained how this equivalent area of the steel in compression arrived. So this becomes stress into area of steel. So this becomes the value of C. Similarly, when we talk about the tension force T, so this will be again written as stress into area. So stress experienced by AST2 will be the sigma ST or FST. So I'm writing here sigma ST into, this again I'm writing as sigma ST by M, because this will be the equivalent stress in the concrete area, multiplied by the AST2. So AST2 formula we can put here. So this formula can be put here to calculate the value of ASC with this relation. So I have simply provided the relations here. So here we are talking about the auxiliary section. So as you can see, CNT I'm using here also, and CNT I'm using here also, but this CNT is for the singly reinforced beam, and this CNT is for the auxiliary section. So here we are talking about the auxiliary section only. So there you can see, so this part is the C and this part is the T. So by equating this, we can find out the ASC. There is another way to find out the value of ASC. Well, in the relation, FCBC dash will also be unknown value, but this can be calculated by using the similar triangle property that I have used in the previous lecture. So you can refer to that. So in the second way, to find out the value of ASC, in that what we can do is we can equate the moment of equivalent area of compression steel and about the Na to the moment of equivalent area of the additional tensile steel. So in this case, what we are doing is we are actually calculating the moment of area about the neutral axis for tension steel and for the compression steel, and simply then we are equating that. So using this diagram I am writing here. So what I have done is this red rectangle is showing the equivalent area of the ASC in terms of concrete, and this rectangle is showing the equivalent area of concrete in tension. So equivalent area of the compression steel, we can we know that this will be the value of for that, and equivalent area of the tension steel in terms of concrete, this will be M into AST2. So calculating the moment of area of these two area about the Na and then equate them. So how do we do that? Well, area of this equivalent area of compression steel, and CG of this area will be something here. So the distance between the Na and this distance will be D minus D dash, because you can see here D dash will be passing through the center of the equivalent area. Similarly, the CG of this area will be here. So the distance between Na and this will be D minus XCR. So this area multiplied by this distance will be the moment of area for the tension steel. Similarly, this area multiplied by the D minus D, D minus D dash, which is this distance. That will be the moment of area for the compression steel. So the same formula I have written here. So there you can see this is the equivalent area of the concrete multiplied by the perpendicular distance, and this distance is basically the distance between neutral axis and the CG of the compression steel. Similarly, this time this is the equivalent area of the steel in the tension and multiplied by the perpendicular distance, which is the distance between the neutral axis and the CG of the AST2. So this is how we can calculate the ASC. So this is the second method through which we can find out the ASC. So either we find out through through the A section or B section, we can find out the value of ASC will be the same. So by further elaborating, we can write this relation as for the ASC. So as I said that steps, so till now what we have done is we have found the relations through which we can find out the reinforcement in the doubly reinforced beam. So mostly the steps will be same for the longitudinal reinforcement as we have discussed in the case of singly reinforced beam. So here also they will be applicable, but there will be some rules that will be added in this case. So I am discussing that here. First is the limit of maximum area of compression steel. Like in case of tension steel, we can have maximum 4% of the cross-sectional area of the steel as per IS code recommendation. On the same way, maximum limit of compression steel will also be the 4% of the cross-sectional area of the beam. So this 0.4 times of BD. So this is actually the 4% of total cross-sectional area of the beam. So this is again as per IS code recommendation. I will show you the same in the IS code also. So there in the IS code, you can see this is the page number 47. So on the page number 47, it is written here. the limits for the compression reinforcement. So it says that the maximum area of the compression reinforcement shall not exceed 0.04 times of BD, which is 4% of the cross-sectional area of the beam. So there is no lower limit of the compression reinforcement. There is no minimum limit of the compression reinforcement, but there is a maximum limit that we cannot provide the area of compression reinforcement more than this. Okay, so that is as per IS code recommendation. And also, as per IS code recommendation, it says that compression reinforcement shall be enclosed by shear stirrups, which means we have to provide shear stirrups to enclose the compression reinforcements. Well, like this is the beam, and if we provide the compression reinforcement, obviously there will be the tension reinforcement. So they should be enclosed by the stirrups. So this is what IS code suggests. So we need to provide these stirrups also so that it can be enclosed within that and it can be held properly. And the next changes which is in the steps for the doubly reinforced beam will be in case of deflection. Well, in the case of singly reinforced beam, we used to calculate, we used to check deflection limit by using the L by D ratio. The same L by D ratio will be used here, and along with the modification factor. So modification factor, how do we find out that? I have discussed this in the lecture 11, and here also I will be showing that how do we find out that, because this time this is the relation that we have to satisfy. So in the singly reinforced beam, we used to have this much relation, but as the compression reinforcement is added, so because of that, one more factor is added, which is modification factor 2. So this modification factor 1 is because of the presence of tension reinforcement, and this modification factor 2 will be because of the presence of the compression reinforcement. So this MF2 is added in this relation. All other things are same. So here we will see how do we find out modification factor 2, because MF1 I have already explained. How do we find out that? We will see how do we find out MF2. Well, this relation is actually explained in this clause under point C and D. I will show you that in the IS code also. So there in the IS code on page number 37, you will find this clause 23.2.1. So this clause is explaining the deflection limit check. So in this, we will use point C and D because we are designing the doubly reinforced beam. So in that case, we will discuss about this. We will consider point C and D. So under point C, we will find out modification factor 1 using the figure 4, and under D section, we will find out the modification factor 2 using the figure 5. So I will show you this figure 4 and 5 in the IS code only. So there you can see this is the figure 4 to find out the modification factor 1, and this is dependent on the amount of tension reinforcement, which means AST. And to find out the MF2, we will use this second diagram, which is figure 5. So this will be modification factor for compression reinforcement. So simply we need to find out the percentage of compression reinforcement, and then corresponding to that, we can find out the modification factor. For example, if the percentage of reinforcement, compression reinforcement is 1%. So in that case, the corresponding value of modification factor 2 will be 1.25 approximately. So this is how we will find out the MF2. MF1 I have already explained how do we find out that, and also when I will be solving the problem, then we will see how do we use this graph to calculate the modification factor 1 value. So MF1 is the modification factor for tension reinforcement, MF2 for the compression reinforcement, and these are the graph that we will use to find out the MF1. So this will be for MF1 and this will be for MF2. So in the example, we will see how do we find out that. So we will continue our discussion in the next part. Thank you.